Okay, so welcome back, everyone. Today we're going to continue our discussion of classification, but in particular, we're going to focus on how do we actually learn the weights for something like a linear classifier that we talked about last time. And in particular, the model we're going to discuss is this model called logistic regression, which is going to be how we learn these weights for making classification. So a lot of the things we're going to learn today about logistic regression are going to tie in very, very closely to what we talked about with a linear classifier. But now we're going to be able to talk about how do we learn the weights, and we'll talk about how there's slight differences and kind of what assumptions we'll be using and how we make predictions with our model. Okay. So as a reminder about where we are, right now, we are working on trying to come up with a classifier. And the case study we're looking in particular is looking at sentiment of sentences. So particularly, we're taking a review about some product or restaurant that says like the sushi was great. And we want to predict using a model we derive whether or not that was a positive review or positive sentiment review or a negative sentiment review. And the idea being that we have some input that's a sentence, write out sentence. But as we've discussed before, machine learning works very well or is defined really well for numeric data. It's not defined so well for words. So we have to come up with some set of features that are numbers based on these words. And the simplest idea we came up with last time is just word counts. So the features we'll use are the number of times awesome appears, or the number of times awful appears, and so on and so on. So we're going to have a feature for every single word possible, or at least word that we've seen in our data. And then the value for that feature is going to be the count of number of times that word appeared. And then we'll feed those features into our model that will then make predictions based on that. Positive sentiment. As a reminder, when we're talking about classification, if we're predicting one of two labels, we call this a binary classification task. There's only two options for each example, and so we call this a binary classification task. Now, last time we introduced kind of a better idea of how to actually try to model this, which was talking about a linear classifier. So for the linear classifier, we learn a set of coefficients for each feature. We evaluate the coefficients, which the feature values for an example. That gives us a score, and then with that score, we make some prediction, either a positive or a negative. So as a reminder for the linear classifier, we said, okay, I'm going to define the score of an example to be the weighted sum for all of these coefficients we learned times the jth feature for this sentence. So remember, the features, or feature J, is going to be the number of times word J appears in the review. And then W hat J is the estimated coefficient for that feature. So it's just kind of like a linear regression. That's why we call it a linear classifier. But we use the score that we come up with to then make a discrete prediction, positive or negatives. The trick then is, how do we learn these coefficients? But scores for positive sentiment reviews tend to be high, while scores for negative sentiment reviews tend to be low. So if it's positive, we want it to predict positive. And if the score is negative, we predict negative. Just as one more reminder, because we see it all the time, we sometimes use this compact notation, W transpose H of X, to refer to this sum of weighted products that I have on the left hand. Whenever you see that, that's just shorthand for writing up that sum. And so I don't want you to freak out when you see it. You don't need to understand where that comes from. It's just an alternate notation. And so what I want to focus on in the rest of this video is how do we actually learn these W coefficients from the data directly. Now, before we get there, the one other thing I want to quickly recap is, how do we actually interpret or think about these kind of decisions that are being made by a learned predictor? So the example we went through on Monday was talking about just considering two feature models of number of awesome, number of awful. And suppose we learn some coefficients. Each example that we might give it, each review, is going to be defined by its place in this feature space. Number of awesome, number of awful. In this example, those are the only features we care about, but you can imagine in real life, you have lots and lots of words. It's a very complicated example to visualize. But each review is going to live in this space of number awesome, number of awful. And then each point is going to get a prediction, either positive or negative. And the way to visualize those predictions is to think about the decision boundary, which is the place where all of the scores from our learned predictor are exactly 0. And then on one side of this line is going to be all the negative predictions, and on the other side of this line are all the positive predictions. This is just showing exactly where the score is negative, positive, or 0. And then our decision rule says from there whether or not you should predict positive or negative based on that. You might be worried about the case where score is exactly 0. What should you predict there? That's just a tie-breaking thing. Either predict positive or negative. The likelihood of getting a score that's exactly 0 is very small. So generally, you just tie-break somehow. I think in the last slide, I said if the score is greater than 0, predict positive. That means if it is 0, we predict negative. But you could do whatever makes sense in your context. So we have this decision boundary. Okay, so now I want to focus on, for the rest of this video, is how do we actually learn the weights W hat? So I think a very good starting point, of one that you probably might think of, is, well, so far what I know from machine learning is I find the coefficients that minimize my notion of error. So we define a quality metric and we try to minimize that. So in the example of classification, I think this is a very good starting point. But remember, for error, we define classification error. It's the fraction of points we mislabel, instead of being something like residual sum of squares, right? We talked about last time that metrics for classification are things like accuracy or things like error. And it's just the fraction of points mischaracterized, mislabeled. And remember, we use this like little I notation to be an indicator. It's 0 or 1. Depending on this event inside of it's true. So every time we make a mistake, this is a 1 that we sum up, and that's going to give us the total fraction of mistakes we make. And so our idea then is just find the W that minimizes the classification error on the training set. I think that's a very great starting point. A lot of times whenever we're defining ML models, we're just trying to minimize notions of error, and that hopefully gives us a good result. Unfortunately, this won't quite work out in the way that we wanted it to. And it has to do with the shape of this quality metric. So for example, just for simplicity, assume that I'm trying to find the coefficient W1. Suppose W2 is fixed. I already know what that is. We're just going to say for simplicity, I'm just trying to search over the space of W1. It turns out that this quality metric, the classification error, is not a very nice function to optimize. In fact, it's very difficult to optimize because it's not continuous. So let me show you what this quality metric looks like, and then I'll explain why it looks like this. So again, this is just trying to minimize W1. We're ignoring W2 for just a second. Suppose we know it, or it's just some fixed value. This is just plotting what is the classification error for different settings of W1. And you end up getting a graph that looks kind of like this. It looks like a staircase that goes down and up. It does not look like a nice smooth curve that we were familiar with from residual sum of squares. Now, a key question you probably have is, why does it look like this? Why is it not this nice smooth function? Well, let's look at some particular settings of W1. So for example, if I set W1 to be exactly 0, that corresponds to the setting of W1 down here. And then we have some, high error. Okay, well, what happens if I increase W1 slightly? Maybe if I increase W1, so now it's something like here. This is a different setting of W1. Maybe the setting for W1's right here. Well, in this case, my classification error has changed, right? I've now made a point that I predict correctly, and I get all the other ones wrong. So I still have high classification error, but slightly better than the old model. So this decreases my classification error. And so on and so on. If I try another model, maybe this yellow model, W1 like here, that corresponds to this point of classification error. I made no mistakes on my labeled data. Maybe if I consider that actual black line here, using that as a predictor, that might also have 0 classification error. This one, maybe up here, trying a different W1, might also have 0 classification error. And then going up and up again, if I keep trying higher and higher Ws, like this one, that one might have high classification. If I imagine this process of calculating classification error for every possible line I could use, we'll end up seeing these jumps in the quality metric, where it jumps from one spot to another, and you end up with this kind of stepwise function. The reason for this is because an indicator function for whether or not you get it right or not is not continuous. If you slightly change the line, so now it gets one example right where it wasn't before, that's now a jump in accuracy, or in this case, error. That will now jump down because you got one more example correct. It's not a smooth process like with the residual sum of squares, where if you got closer and closer to the point, you incurred less and less error. It's either you're right or you're not, according to this quality metric, and it causes these discontinuities or these steps. So this makes optimization algorithms like gradient descent quite difficult because you don't quite know where to go. Like, for example, if you look at all of these predictors, they all live on a same flat line. Gradient descent can't tell you do you go left or you go right. There's no slope there. The slope is 0. There is no well-defined slopes at any of these points that aren't 0, because they just have discrete jumps down every time you make a new prediction correct, or one less one incorrect. So this classification quality metric, while very intuitive for what we might try to minimize, tends to not actually work. And this slide is just kind of summarizing all of the things I just said, where minimizing classification error is totally the intuitive thing to do, given everything we've learned about regression, but it just doesn't work with classification. We aren't able to use methods like gradient descent because this function's not nice. It's not differentiable. It's not continuous. It's not going to let us roll down this nice smooth hill. So instead, what we're going to do is we're going to define a new quality metric that's going to be a stand-in for classification error. So we'll use one that lets us, in some sense, be something that's close to classification error, because that's the thing ideally we want to minimize. But it's actually going to be we're going to be able to use an optimizer on it. We're able to actually take a gradient, roll down a smooth hill. And so the way we're going to think about this is going to be kind of strange at first, is we're going to try to switch perspectives. Instead of thinking about discrete predictions, think about probability predictions. So at a high level, trying to say, I think it's very likely that this review is positive, maybe with 99% confidence. And we're going to think about our perspectives in terms of that, instead of thinking about yes, positive review or no, negative review. And to do that, we're going to have to talk a little bit about probabilities. So here, we're going to be thinking about the probability of a review having positive sentiment given the words in the review. So we're going to assume that, in particular, one of the reasons why we're going to think about probabilities is we're going to assume that there might be some randomness in the world. That instead of saying that there's an exact function that says, oh, for this review, it's going to have this sentiment, we're going to say for this review, it's probably going to be a positive review, or more likely than not to be positive than negative. And so we're going to switch our model around to think about these things in terms of probability. Okay. Now, what we'll do is, for an example, like the sushi and everything else were awesome, we're going to think that that's very likely to be a positive review. And so we might want to output that the probability that it's a positive review is something very high. Now, as a reminder, if you haven't seen this before, we're going to be thinking about this notation that we call conditional probability. So the way you read this notation, say something like the probability that y equals +1 given x equals to some review is saying, what is the probability of getting a positive sentiment label conditioning on this one particular sentence we saw? This conditioning is kind of important in terms of actually making these definitions. If you just ask what's the probability of a positive review, you might just have to look at the statistics over the whole data set and just say, oh, like 3/4 of them are positive. But this is saying, what's the probability of having a positive review if you know the review has these words in it? So this conditioning is restricting yourself to just looking at this one review and then asking, what do we think the probability of it being positive is? And so that's what this notation is trying to say. You can also, and so since these are probabilities, these are going to be numbers between 0 and 1, where 0 is very unlikely and 1 is extremely likely. And anything in between is degrees of certainty. So you might have another example that says, like, the sushi was all right, the service was okay, where it's more ambiguous. Is this a positive review or a negative review? In which case we might say that the probability it's positive or the probability it's negative might be something like 0.5, because we're not quite sure. Is it a positive review or a negative review? So this gives us some flexibility that we can have uncertainty, and then we can also show degrees of confidence, where that first review seems very, very likely to be a positive sentiment review, while the second one is, it can go either way, so it could be either. And so we're going to use probability as the measurement of our certainty. The higher the probability of it being a positive review, we're going to claim we're more certain that it's a positive review. Now, I want to clear up, in case you haven't seen this conditional probability notation, I want to highlight a couple other things. We'll sometimes use this notation py given x to mean p x to mean either probability that y equals +1 given x if y is equal to +1, or the probability that y equals -1 given x if y equals -1. Or otherwise. So we're talking about what's the probability of seeing the true label y given this particular input for its review. And this is really a statement of, is it positive or is it negative? What's the probability of actually seeing that? Okay. So we define this as a conditional distribution. We don't really worry about that too much, but this is what I mean when I say p of y given x. It says, what's the probability of seeing this y given this x? One other thing that's good to note is that the probability that y is equal to +1 given some input x plus, I'm writing? Okay. Plus the probability that y equals -1 given some x must be equal to 1. In this case where we only have binary options, it's either positive sentiment or negative, the probability of seeing positive plus the probability of seeing negative should be equal to 1. And this is also true when you condition. You condition on x for both of them, those also should form a valid probability distribution, so they should also sum up to 1. And so that's why you'll sometimes see us kind of mix up. Are we talking about the probability y is equal to +1 or the probability y is equal to -1? Both of these given the review is because they're related. You can always figure out what's the probability that y is a negative review by taking 1 minus the probability it's a positive review. So there's a lot of kind of ways of interoperating between. So what we're going to do is we're going to come up with a probability classifier. The idea is try to estimate what we think this underlying probability distribution is, the probability of seeing y given the review x, and use those estimates of probabilities for a prediction. The idea here is we're going to try to estimate what we think the underlying process, the model of the world that says for this review, how likely is it going to be a positive review? And we're going to try to estimate what those probabilities are using a model and trying to learn a predictor under that. So the probability classifier is going to estimate this probability that y is equal to +1 given x. And then we'll come up with a rule that says if it's more than 50% chance of being positive, we'll output our estimate of y is positive. Otherwise, we'll output it as negative. Note, this is incredibly similar to the notion of the linear classifier with a score. But instead of coming up with this arbitrary number for the score, we're going to try to come up with probabilities, saying that it's very likely to be a positive label, but because they're probabilities, they must be constrained between 0 and 1. They can't be arbitrary numbers like the score was. And this is going to be very helpful for one note, is that now this kind of thing we're predicting, these probabilities, they're interpretable. Like before when we talked about the linear classifier and I said you got a score of 207, that doesn't really mean anything other than that score was positive. But now if we set up our model correctly and it outputs, hey, I think the probability is 0.97, then we know it's very confident that it's going to be a positive label. I think there's a 97% chance of that. Okay? So this could be a very nice thing for interpretability. So to kind of visualize what we're doing, we're going to relate the score that we found earlier to probability. So it's actually going to be the case that the probabilities we're trying to learn are going to be very closely tied to the score. And we're going to do this for one, in some sense, simplification. There are lots of different models that try to model these probabilities differently, but we're going to make some simplifying assumptions about the world. And we're going to assume that the probabilities have a sort of linear relationship with the data. And I'll explain what that means. So our big idea is take that linear classifier we talked to Monday, where we learn a score, and somehow take that score and turn it into a notion of probability. So we'll learn some coefficients, like 1 is times number of awesome minus 1.5 times number of awful, and we'll try to relate that score to a probability statement. So if the score that we find is positive, we're going to relate that to the probability. That's saying that the probability of seeing a positive sentiment there, given that x, is going to be greater than 1/2. So if it's a positive score, we want to associate that with a greater than 50% chance of being a positive label. What if the score is negative? Well, just the opposite. Then we're going to say that the probability of y being -1, given x, greater than 1/2, which is equivalent to saying that the probability that y equals +1, given x, is less than 1/2, right? Because these two things must add up to 1. So we'll say that the probability of being positive is less than 1/2. And then what if the score is equal to 0? Well, then we'll say the probability is 50-50. It's exactly the same chance of being positive or negative if the score is exactly 0. So we're making a mapping from scores to probabilities. Again, I haven't told you how to find the coefficients. We'll get there, I promise. But we're going to say, okay, well, I somehow learned a model, and I want to take those kind of scores we outputted on Monday and turn them into something more interpretable, turning them into these probabilities. Now, the exact mechanism for how to do this, I haven't shown you yet, but we'll get there. But now what we're kind of doing is we're making a mapping, taking the score for the ith example, which will be a number between negative infinity or positive infinity. It's going to be a real number. And in the case where the score was really, really large, we maybe had this intuition that we were more confident in its prediction. If the score is ever positive, we predicted +1. If the score is ever negative, we predicted -1. But we used that score in that prediction last time. And now what we're really doing is we're just trying to assign degrees of certainty. That if the score is very, very large in magnitude, we're very, very certain, and the sign still determines whether it's a positive or negative example. But if it's near 0, we might not be as certain, and we want to quantify that. And so what we're doing now is we're taking a mapping from these scores that we came up with before to probabilities between 0 and 1, where if the score is 0, we want it to be around 50-50. If the score is near positive infinity, we want it to be very close to 1. And if it's near negative infinity, we want it to be very close to 0. We want it to say it's very unlikely for it to be a positive review if we came up with a very negative score. So now all we really need to do is define a mathematical function that lets us go from scores to probabilities. And before I show you this function, I want to highlight, again, I have yet to show you how to actually learn these coefficients. All I've shown you is suppose I had some coefficients that gives me a score function, and now I'm taking scores and translating them to probabilities. And the reason I'm doing this is that this new thing in terms of probabilities will now give us an algorithm to learn the coefficient. But we'll get there, and we'll particularly talk about that part in class. Right now, I'm just setting up the model. So now the last thing I want to introduce today is what is that function? What is the function to translate between scores and probabilities? And we'll use this thing called the logistic function or the sigmoid to do that. It's a function that is defined for any real number input and maps it to an output between 0 and 1. Now, you don't need to know where this equation comes from. People decided that this is the right equation to map values from negative infinity to positive infinity down to 0, 1. There are other such functions, but we're going to be talking about this one in particular because it leads to this thing called logistic regression, which is a very popular type of model. The idea is you use this thing called the sigmoid. And the sigmoid function looks kind of weird the first time you see it. It's 1 over 1 plus e to the negative input. I think it looks a little hard to see it when I'm also talking about scores, but more generally, if you're talking about what's the sigmoid of some value z, this is 1 over 1 plus e negative z. But in this case, because we cared about scores in particular, I'm treating the score as the input, but you can see those equations are the same. What does this equation look like? Well, it looks like this nice kind of beautiful S-curve, where if the score is very, very negative, the number is close to 0. And if the score is very positive, the score is close to 1. And if the score is 0, the output is 0.5. So let's think about what the shape of this function actually results in. Imagine we plugged in a score that's really, really big, like close to negative infinity. Well, in that case, we have sigmoid of 1 over 1 plus e, the negative infinity, right? Because it's the negative z. Well, negatives cancel, so we have 1 over 1 plus e to the infinity. E to the infinity is probably a really, really large number. E times e times e times e times e. That's going to get really, really large. And since the denominator is going towards infinity, then the numerator is going to go to 0. Or sorry, the whole fraction is going to go to 0. So when the input you give it is negative infinity, this equation works out to be 0. And that's part of the reason why there's that negative in that. Now, on the other extreme, what if you did something like positive infinity? Well, this would be 1 over 1 plus e to the negative infinity. Remember, there's that negative sign in the equation. Well, remember that powers to the negative is the same as 1 over that thing. So 1 plus 1 over e to the infinity. Well, in that case, again, e to the infinity is going to very, very large. It's also going to infinity. So 1 over that 0. This goes to 1 over 1. This is why when the score is very, very positive, it's something closer to 1. Let's try a couple of other examples of actual numbers because these infinity conversations can sometimes be kind of hard to follow. So let's consider a score of 0. So if you have a score of 0, your sigmoid is 1 over 1 plus e to the negative 0. Well, e to the 0 or e to the negative 0, that's the same. That's just 1. This is 1 over 1 plus 1, which then 1/2. The way to visualize this is that when you give it an input of 0, the output is 0.5. That's what the sigmoid said. It's just defined in this way so that when you give it a 0, its output is a 0.5. What happens if you give it something like negative 2? Well, if you give it negative 2, then we would expect the score or the probability to be less than 0.5. Let's just make sure that math works out. If you plug into your calculator 1 over 1 plus e to the negative 2, that ends up being something like 0.12. Which is kind of what we were expecting. It's a negative number, so it should be less than 50% chance of being positive. So then it's going to output 0.12, or whatever your calculator said. Alternatively, if you tried a larger number, like the score being equal to 2, then we would expect from this graph that it is more likely for it to be a positive output. And so if you plug this into your calculator, you get 0.8. So the sigmoid is just a function someone defined to take an arbitrary score from negative infinity to infinity and output a number between 0 and 1. And this score, or this way of transforming the score, is very important. It's called a sigmoid function, or the logistic function. And this is what defines what we call the logistic regression model. So the logistic regression model is modeling the probabilities of things happening. So we're saying, what's the probability of this positive sentiment, or this review being positive sentiment, given this review? And now we're saying, okay, we're making the statement. We think the world works, that this probability is controlled by a linear function that determines score. And then we map that score to a probability between 0 and 1, using in particular the sigmoid function. And just as a reminder, remember that score of x equal to whatever coefficients we learned times h of x. And so we just plug that in here. So for any setting of w, the probability of this output being positive is defined by this function. Calculate the score, feed that into a sigmoid, that gives you a number between 0 and 1. And so now our modeling task is given a review, estimate these probabilities, probability of y being +1 given this review, and find the coefficients that make this probability match up the most with kind of what we saw in our data, that we want the probabilities to line up such that when it was actually a positive review, the probabilities we output are close or above 0.5. Otherwise, they're and we use the sigmoid with our score to predict that. Again, I have yet to tell you, and I keep putting this off, how do we actually train these W's? How do we find the right W? That's going to be the first thing we talk about in class. But here I've just set up a model where it's just like the model we talked about on Monday, where it's a linear classifier that outputs scores, and we use those scores to make predictions. The big difference is we're also saying that, hey, we want to map these to probabilities, and we just take those scores and apply sigmoid. So then it squishes the number between 0 and 1. And then now our big task that we'll tackle in lecture is, how do I actually learn these W's? And why did this help us? And we'll find that switching to probabilities makes the problem smooth, but then we can use something like gradient descent. But we'll cover that in lecture. But we switched models now to think about these things as probability. And just to kind of highlight where this lives in the ML pipeline, we are now changing our ML model. That we're assuming that we're trying to predict kind of this thing that follows these sigmoids or these probabilities, and we'll use this kind of probability in our ultimate predictions. This is the things that we're predicting with, is these probabilities. And next time, or in class, I will talk about how do we define our quality metric and our ML algorithm to now learn these W's. But this is all I have for this video because it's already running a bit long.